multiplication story. Actually, I'm running a bit behind with the schedule, but it's always like that when you want to explain the homework as well, but I understood you appreciate that. It's good work, then I'll do that. Then we looked on how to do multiplication faster. And then what we saw is there are a couple of things which can help. One is to do things in higher radix. The higher the radix, the better, because you consume more bits in the multiplication process, but this is complicating the generation of the partial products. And in order to do that generation, you can do recalculation. Remember the 3A guide that we kind of avoided in many ways. If you go for higher radix, you will have also 5A, 7A, and then 6 will get, more complicated. And in order to deal with that, we mostly rely on multiplexers. Then you inspect bits from the multiplier, and depending on the value of that bit, you select A, 2A, 4A, 8A, if you inspect more. And then with the tree of carry save headers, you actually combine those numbers and you obtain the right partial product. Then the second part is to accumulate those partial products between different iterations. And we look initially in the not very smart solution, which was to propagate the carry in each and every iteration. And we saw that that one is not really a brilliant approach. And then we said, okay, what we can do is instead of computing the accumulated partial product as one number, we keep it as two numbers. And essentially, if you do that, you have a tree, a carry save header tree, which will have a number of stages depending on how high the radix is. Because if I inspect more bits, I will have more maxes, and then I have to combine them eventually down. And then there are the two numbers coming from the previous iteration, and this is the cycle time. It's determined by that. In all iterations but the last one, I do not propagate carries. I just do accumulations based on full headers. There is the other story which relates to the data flow. If I consume more bits, I have to report for output more bits. When I do that report for output, when I'm propagating the carry, there is no complication. When I keep the accumulated partial product as a two number, then I have to add this header here, which will take the bits which are going for output, will propagate the carry, and will keep a carry for the next iteration. If I consume more, I have to add more. And then eventually, I may end up in this part to dominate the calculation and to impose the cycle time. What I want is I want a beautiful cut, a brilliant cut, when the delay of this and the delay of that are the same. In here, if I look now at what I have, this is a 2-bit header, which is 2 ripples, then 2 full headers, and in here I have 2 full headers and some maxes. Then this is still dominating. Now, having that in mind, I understand what the basic principles are, and I can play with higher radix. Then radix 8, radix 16, radix whatever. This is a radix 16. Then I am inspecting 4 bits at a time. Then I will have the number of bits divided by 4 cycles. What do? Based on each bit that I'm expecting, I'm selecting A or 0. And A with the weight, which is determined by the bit. Then I have A to A for A, 8A. If I go further, I will have 16A. Now I have more values here, and those values have to be reduced. And because I have 4, what I'm doing, I can have a nice tree. Then 3 of them, I attach them to a carry save header. 1 together with the previous value it's another carry save header. Those are producing now things for output, and in 1, 2, 3 stages, I'm done with the reduction. Then I extended the radix, then I have more numbers to compress, then my tree is deeper, and then I have now 4 bits for output. I already see that this is now kind of dominating the delay, because this is a 4-bit header. If I don't do any kind of smart implementation, it will require 4 full headers delay, in the worst case. And while here I have 1, 2, 3, plus the maxes, then this is somehow faster than this. What we do in practice is we use a different implementation, and for such a small full header, I can build a lookup table. Then I have the inputs. There are 4 bits, and I have a lookup table. I use those bits as address, and from the lookup table, I read the result and I read the key, right? It's getting larger, but it's still doable. Depending on the technology, I may rely on that or not. Most likely, if I try to build another header which is fast, won't really help a lot. If this is not a good design and I don't like it, it might be better to diminish the radix and to go for 3 bits at a time. And as long as I understand where the trade-offs are and where the consequences of my decisions are, I can optimize my design. Okay, then this is how you actually do the reduction. Then if you go for less, you get some, make this smaller. Now, generally speaking, I know one thing, that propagating the carry in each and every iteration is bad. Then I should not consider that in practical cases. But in this domain, I have a lot of possibilities. I can do serial with or without propagating the carry, but it's better without, because each iteration will be faster. I can do full tree, which is 1 iteration now. I'm doing radix. The radix is as large that I'm considering all bits in one shot. And this is the full tree design. This is the fastest one. How do I do that? I rely on whatever I know from Dada and Wallace. I made the reduction of those partial products to 2 rows, and then I do the final header. And then I have solutions in between. Now the difference between smaller tree and high radix is blurred. Because essentially what we saw, in here, this is a tree, okay? When the radix is kind of small, I can think that this is a high radix multiplier. When the radix is getting high, then this tree will be the dominant guy, and then I will see it like a partial tree multiplier. It's a matter of terminology, but at the end of the day, the difference is between considering few bits at a time or many bits at a time. Okay. And in this domain, I can play the way I like and play. What is very important is that in order to have performance, I have to rely on carry save headers. If I don't do that, I'm kind of slow. Now, slow is not necessarily bad. If I have a lot of slow designs, slow units, a lot of them, which are working in parallel, and I can feed them with enough data to do calculation, this is also not a bad approach. But if my application does not have enough parallelism, such a decision will not be good. Okay, now this is a kind of different way to improve the speed. And it relates to probably something that you know, like the master-slave flip-flops. Okay, in the Netherlands you have a lot of locks. Okay, the sloughs, which is connecting to rivers, which do have difference in level. Okay, you know what the lock is. There are two gates, and you open one, you close it, you open the other one. That's the principle of the master-slave flip-flop, which is separating, you know, this is a normal flip-flop. Whenever you have input, you sample it on the rising or on the falling edge of the clock. Then if you sample it on the rising edge, nothing will happen until the next one. If you have a master-slave flip-flop, one is sampling on the rising and the other one is sampling on the falling edge of the clock. Then you use in your system this transition and this transition on the clock as references. Then somehow, even though the frequency of the clock is the same, your operation speed is twice as fast. Do you get that? Then I'm not changing the frequency of the clock. The clock has the same frequency. But instead of doing things only on the rising edge, I'm also doing things on the falling edge. But on different hardware, not on the same hardware. Then this one, this one is working on the rising, and this one is working on the falling. Now, having that in mind, we can build a structure which is like that. Then each of those guys is doing radix 8 multiplication. There is, to make life complicated, there is even with booth recoding, but it doesn't have to be with booth recoding. What is happening is that I am taking 3 bits at a time, and there is a kind of rotation. I start doing work on 3 bits, and in the same time I start doing work on the next 3 bits. But there is a kind of shift in time between us. Then whenever I'm kind of done with the calculation in here, I'm ready for this to proceed. Then there is an overlap between stages. I'm computing as I would have consumed 6 bits at a time with less hardware and less complexity. Then, you know, I'm reporting for output 6 bits at a time, but they are coming from different sources. And at the end of each cycle, I'm ready with these guys. Then I am working with the frequency, which was my nominal frequency, but one of the multipliers is working on the rising edge, and the other one is rising on the falling edge. Okay, and you can even push this to what is called the multiple bit multiplier, but I mean, this is more theoretical stuff. This you can do in practice. There are things, however, which you have to be careful about. You may have races, you may have glitches, because when you start the calculation in this one, you have to be sure that this one is available. If this one is coming a bit later, then you may produce wrong results. But the beauty of the scheme is that you obtain a performance which is actually for a higher radix without increasing the hardware in the linear way on the radix. You just double the hardware and you obtain the same kind of performance. And this is a trick which relates to this overlap. And the fact that you are not increasing the clock frequency is good because you are not consuming more power. When you have your clock running faster, there is more happening on the clock, you know, charging, discharging the clock lines, and this results in more power. This design is consuming 6 bits per cycle and is producing 6 bits per cycle. But I'm consuming them in 2 portions. I start with 3 bits in one, and then with 3 bits in the other, and eventually I complete the design. And the cycle time is reserved. Okay, now this is about the complexity of VLSI circuits, and eventually, you know, if if you do a radix 2 power something multiplier, you will need a number of gates to generate the products. Those are AND gates. Now, if you could do the generation of the partial products with a different technology, and you could embed, as you were saying, if you can represent digits directly in hardware, those will not be any longer AND gates, will be some other kind of multipliers, right? But because the easiest solution is to rely on binary representation, you have that kind of number of AND gates, then you have a reduction tree, and then you have the final adder. And this is, you know, standard approach for fast multiplication. I won't go into this too many details. Now, we were discussing about this, and this is my solution space, and this is actually the fastest design that I can do. And the fastest design that I can do will require the production of the partial products, which is this, the reduction of those, and the final conversion to binary. We call this redundant to binary converter. There is no real redundancy in the representation because I still deal with binary 0, 1. The redundancy is coming from the idea that I'm representing the number as two numbers. Now what I see is that even though my product is twice as large as the multiplier, some of the bits are going out of this conversion. Then my final adder does not have to be as wide as 2K. And in some designs, what I'm doing is I'm using the normal adder in my system, which is the width of the architecture, in here, and then I'm sharing resources. This is good because you save resources, but if I'm using my ALU, which is the one which is doing most of the work in a processor, then I will not be able to execute a multiplication and an addition in the same time. And for that reason, a multiplier is composed typically out of this reduction, which is a Wallace or a Dada tree, where I will play all the tricks that I can in order to report as many bits as possible the output, and a final adder which is as fast as it gets in my technology. And in this way, I managed to get a processor where addition takes one cycle, and is this cycle, and the rest of the multiplication takes another one. And because in this tree, I can add another value most of the time without any problems, I can compute with this A times X plus B, which is the famous multiply and accumulate instruction, which all or most of the decent DSP processors have. This is it's very often that you have to compute this. Okay. Now, if I do it without support, this takes 2 cycles and this takes 1 cycle, and this will end up in 3 cycles in a processor. Because of the fact that this B can be seen like another line in my partial products, then I can get this in 2 cycles. And this is typical in DSP processors. Okay. Now, if my budget is not good enough to allow me to do such a structure, this is logarithmic because it's 3, this is logarithmic because I cannot do better than logarithmic. I could try RNS, but if I do RNS here, I have to do some other more complicated things. Then I will stick with normal binary representation. Then if I cannot afford that, what I'll do is I will have a partial pre-multiplier. The only difference between them is that this is computing in one cycle and this will require a number of cycles. The rest, the organization is the same. Okay, and this is exactly what I told you, the 3 stages of the full tree design. And in here, it's a very simple multiplier, 4 times 4 multiplier. And now you see if I apply Wallace or Dada, I have different things, and that will matter. Because if I apply Wallace, my final header, it's a 4-bit header, which, assuming that my architecture is a 4-bit architecture, will allow me to complete this in one cycle of my architecture. If I apply Dada, this will give me a 6-bit header. And then I have a problem. This 6-bit header will be slower than the 4-bit header. Roughly speaking, this will consume 1.5 times more delay. And then this will blow up my cycle time and won't be a good solution. Now what you see in here is that I wrote this in this way, which is not a difference. Doesn't matter where I place the dots in position on the rows. What's important is to preserve, you know, the position in columns, because in columns they have the weight. The fact that I'm putting here, you know, when I think about the production of these dots in a serial fashion, the fact that I put here this is because I'm doing the multiplication of this with this, and it is kind of logical to write it in this way. But these kind of products are AND gates which are working in parallel. And the fact that I'm rewriting it in this way is not relevant. What is relevant for the delay, and that will tell me something, is the height of the tallest column, because that will determine my delay. Okay, and the rest you are familiar with this, right? This is telling how many dots I have per column. What I am doing, I'm putting full headers, half headers, whatever, and this is my result. Okay. Now, there is a small problem with this approach, because even though it looks beautiful from the point of view of my dots and my diagram, when I lay out it in a circuit, it is not really regular. And there are two things. One is the logical level, which is clean. And I see those dots which are propagating from one level to the other. And in my drawing, they are really nice and I understand them. And the other story is when I make the layout, when I really make the circuit. And I have to make interconnects. And there are things which are going irregular, and as you see, things are kind of increasing, decreasing. There are bits which are going for output. And in today's technology, this is very important. It used not to be that important in all technologies, because in all technologies, what was important was the delay per gate. Then the gate was the main contributor for the delay and for the area. Today, gates actually consume not very much time. The most important part is to transfer the information from one place to the other. And even on local wires, if they tend to be too long, this can be a dominated delay. And in order to deal with that, what you want to do is you want to create some regular structures. And you see, this is a reduction tree. And from the logical point of view, I will put it like that because this will let me see how I'm doing the reduction. From the layout point of view, what I will do is I will compress them in a column, and that will be a slice in my design. There will be wires going from column to column, but I will put them in such a structure. What I'm trying to do is to create a regular structure in my design, which is very important. And remember, we are talking about 4 to 2 counters, which are very nice for this. And I was looking there for an implementation of the 4 to 2 counters, and I said I saw it somewhere, and this is where I saw it. Then if I rely on population counters, normal counters like full adders or 7 to 3 adders, we had a discussion that I am getting n and I'm producing log n results. And we were discussing about n to 2 counters with this nice example, which is the 4 to 2 counter. And in here I see two realizations. This one is based on full adders. Okay? Then I'm taking 4 inputs, and I am generating 2 outputs for me, and which is 1 for my position and a carry for the next position at the end of the calculation. But I'm also generating a carry in the middle of the calculation, which we discussed last time, that is not delaying the calculation because they are not getting one after the other. This is coming in the right moment. Then, you see, this carry is coming from a previous position, but it's coming when I need it. If I would have route this signal up, then they are, you know, in data dependency. In here, there is no dependency. And now I see, I can implement that with 2 full adders, cascade it in this way, generating what I need to, or I can implement it in this way. And this is faster than that. And because this is faster than that, a 4 to 2 counter will result in a better compression, in a better implementation of the reduction tree. If I rely on this, what I will win is mostly from regularity. If I rely on this plus this, then on this implementation, it's regularity plus some advantage on the delay of the scheme. And in here you have a reduction tree, which is now 4 to 2, and this is also, you know, it's shallower because I'm consuming more inputs than 3 to 2. Okay. Now, this is an example on how do I actually implement that in a practical layout. Then this is the structure when I'm generating all the partial products. I have some broadcasting lines which will help me to do the calculations. You know, this is multiple generation circuits, which are here. And then I arrange them in such a way that they are emulating this structure, you see? These 2 and these 2. These 2 and these 2. At the first level, they can be very close. As I'm going down into the circuit, I cannot put them very close because there is no, I don't have choices in the geography. Then these guys are the first level. You see, they are as close as it gets. And in between, I generate the result. And this is the second level of the calculation, and this is the final level of the calculation. This is helping me to keep things under control and to kind of optimize the delay. It would have been nice to have another dimension in such a way that things are also, because you see, the deeper I go in the tree, the more far away are the contributors. These were closer, now the blue guys are a bit more far away. If I can put them in the top and I can do 3D integration, I can kind of preserve that. But this is not done. I mean, the technology today is not allowing us to do that. And after I finish the calculation, this guy is actually bringing results to the final head, which I cannot put very close. But assuming that I have 2 dies, I can put this on the first die, and from the middle of the die, where is the brown thing, I can take some bias and go in the header which is in the top. And this, you know, from the logical point of view, nothing is changing. But from the physical implementation and from the performance point of view, things may change fundamentally. I mean, today in chips, people are thinking about optical transmission of information from one corner of the chip to the other corner of the chip, or even for placing small antennas, do wireless communication inside the chip. These are not, let's say, science fiction stories. Because the silicon, you know, we can make chips which are larger and larger, and then we have a problem. And 3D integration is a solution. Then you fold things, and then you make them closer in a 3D space. And using other kind of means of communication, like optical communication, can solve other problems. But you cannot send on an optical channel just one bit. You have to have a bunch of, you know, a lot of information to travel. And this is in networks on chip, for example, you can do that. Okay. Then sign extension. Now, my matrix is certainly not nice, and I have to do sign extension. And we discussed the sign extension, then basically I have to pad all my columns in such a way that I obtain that funny shape when everybody is going up to the most significant position. What you see is that when I do this padding, I will have to apply full adders over positions which are similar. And then I have two solutions. I have the solution to make copies of that, then to apply the same full adder n times, or I have the solution to make one, and this one will drive all the full adders which are consuming this result. I think I mentioned that, but I will do it again. Both of them have advantages and disadvantages. And I have to think now in the layout space. This seems to be good, but this box, in order to drive that many outputs, has to be larger. And if it is larger, it may kill my regularity. Then, depending on how things are done, I may go for one or another. What I certainly have to do is I have to do something to deal with the sign in the proper way. And this is sign extension, or things which we kind of know, okay? Those were proposed by Bo Willey, I think in the 70s, when area was an issue, a big time issue. And then there are a number of approaches, but all of them relate to the fact that when you have, you know, a multiplication of digits in 2's complement, whenever you do that, there is negative weight carried on by some of those dots. Then if I am doing the calculation in unsigned, each dot is the result of an AND gate and nothing else. The position, the column will tell me what the weight is, and there is no sign. But when I'm doing in 2's complement, all those red guys, they actually carry a negative weight, which I have to deal with it. I'm not doing sign extension. If I do sign extension, its problem is solved, because all of those guys, you know, will have good things here, and I'm done. But I don't want to do sign extension. And then what I have to do is I have to take into consideration the contribution of those positions in the proper way. Okay? This one in here is not negative, because this is a product of two most significant bits, which both have negative weight. Then this is give me a positive one. But the rest are negative. And now, those guys came with approaches which they said, okay, what I'm doing is I'm replacing those with a bit of extra calculation in the generation of the partial product, and some kind of extra signals which are compensating for that. And this is one approach, this is the other approach. And each of the approaches is based on some kind of simple manipulation which we are familiar with from 2's complement. Then first approach is saying, okay, I have a term which is a4x0 which is negative. I want to get rid of the minus. Then you want to teach? I said you talk too much. Then I will rewrite that in order to preserve the value. If I'm not preserving the value, I made a mistake. And what I wrote there, it's okay, it's not a problem. 1 minus x0, remember, is x0 bar. Because remember that. Then what I have is I replace the negative value with a positive 1 and a negative 1. Now the negative 1 again is not good. Then I will take the first position and I will say the first position, which was minus a4x0, will be a4x0 bar instead. And in here I have to write a minus a4. Minus a4, it's negative again. I don't like it. But I write it like minus 2a4 plus a4. Then it is an a4 which will stay in this column and a minus a4 for the next column. This is the same trick which I'm using quite often. When I don't like minus 1, I'll write it like minus 2 plus 1. Minus 2, it's a carry into the next position, which is a minus 1 there, a 1 here. And what I will do using this, I will replace all those negative guys with what corresponds, and then I will have here some extra values. Okay? Then in here, because I have 2 negative terms, I will have an a4 and an x4. Okay? And then whatever is negative, I will propagate out of my domain of interest by playing that kind of games. And this will provide me such a structure. And I can do it in this way, or I can do it in this way. Then they are based on different kind of implementation. Now, do you have idea which one is more convenient, is more interesting? This one? Why?
Because you can hide the ones in the tree later, and you can negate both of the values, and you have less layers of the previous one.
Then in here I have an AND, right? Then it's just in one gate I'm solving the problem. Instead of computing AND, which anyway it's complicated because I have to do an AND and an inverter, I obtain this with an AND. Now, what is here, you know, I have this extra 1 in here, it's a constant. But it will still contribute to the reduction, even though it's a constant. Then there are 2 aspects in here. One is the effort that I put in order to do the rewriting and how I compute those additional terms. And in here I see I can compute it directly with an AND gate, while there I will need an inverter and then an AND gate, which in CMOS is equivalent with having, you know, an AND and after that an inverter. However, this may not be necessary if I absorb that negation in a later on calculation. And I can always play with Boolean algebra, and instead of considering as it is, to consider the inversion, and then, but I have to redesign the next stages. And that's one story. And the other story is the amount of extension that I'm bringing to the column. And if the column is getting higher, and I am within the boundaries of the beautiful numbers in that table, there will be no consequences on the reduction tree. If the height of the column is going from one interval to the next interval, I have a penalty of 1 full adder in my design. And then I should think if I really want to rely on this, or I should apply another solution. Okay? This is a way which, you know, to understand it in a different way now. There is something else, and that maybe is good to talk today. It's about multipliers, which are now on fractional numbers. Then when I multiply two integers, what is happening is that the dynamic range is increasing. Then I multiply two integers, and my result can be now a lot bigger. When I multiply fractional numbers, what is happening is that my partial product matrix is actually not going towards larger numbers, it's going towards more precision. Then while for the normal multiplication of integers, my partial matrix was looking like that, and I had, you know, to accumulate everybody because my reference was here, and then I'm increasing the dynamic range. If I do that for fractional numbers, I'm going into the other direction. And what I obtain is I obtain a lot of dots which are actually in a position which is smaller than my unit in last position in my architecture. And now the point is, what should I do with those? My architecture, it's an, what is this? It's an 8-bit architecture. Then I have 8 bits, and all of them are utilized after the decimal point. Now, I have a lot of bits here, which do have weights, which are smaller than this. And what should I do with them? Should I try to compute them all, and then make a precise result? Or should I try to do something else? You know, if I add all of them, assuming that I drop all of those, my maximum error will be 1.7 unit in last position. Okay? Because I will compute, you know, all of those. Remember, 2 to the power minus 1, minus 2, minus 3, all of them are going down. Then, you know, the fact that this is in the fractional part will not preclude me to apply here full adders. Full adders don't see that. But my effort will give me a result which is contributing with at least, at most, let's say it's less than 2 units in last position. And I will spend a lot of hardware in here. And that's the reason why, when we deal with fractional numbers, we don't really do that. What we say is, we just drop those guys, and we do some compensation. And, you know, these are some compensations. I completely drop, and I put a 2 in here. Or I drop, and I put some of those guys here. And I will have an error, which is now larger. If I completely drop things, then I can end up in having an error between 4 to minus 3 units in last position if I apply this technique. If I apply this technique, you may try to guess how many units in last position I'm losing. Essentially, there is a big difference between the first and the second, because this one, it's a compensation which does not depend on the operands. I'm just dropping all the bits here. I put a 1 there, and then I do the reduction and undo my calculations. And in this one, I drop everybody here, but I put some of the bits which are there in my calculation. Then this is an adaptive compensation, while the other one is not an adaptive compensation. And this, it's a complex problem, and people in the community are dealing with that, and there is still research going on in this direction. Now I have 1 more minute. And in that more minute, I will say something about what is called array multipliers. These are Then when I make a tree multiplier, what I want is to have a fast design. This is actually a degenerated tree. Then I am taking all the inputs into consideration, but I'm adding one at a time. Then I'm not pushing parallelis to have a real tree, but I am taking them, you know, in pairs. Then I'm adding one more partial product. It's the same philosophy. Then I have all the partial products, I'm applying a reduction, but now my reduction is not a real tree, it's a degenerated tree, and I have a final header. And this will result in such a structure. Then in here, those are the reduction parts, and here this is the ripple hairy part. This is a very slow design if you compare with a normal tree. Because I'm not using here a fast header, I'm not using here a tree. It's a degenerated tree, it's linear. Now, why do you think somebody had such an idea? Yes?
You can make kind of like a pipeline.
Yeah, it's very well for pipelining. And next thing, it's very regular. These boxes are all the same. Those are full headers. There are local interconnects. There is no long distance interconnects. You see, I only connect with my neighbors. And even though it's slow, because the critical path is going, you know, downhill here and then on this header, which is downhill on this diagonal and then on this header. And it's not fast. It's regular, connections are short, and I can pipeline it. We'll talk about that next week, Monday.